fine. Okay, so it should be recording, and I'm gonna try to sort of film that bit.
Okay. Sorry, did you send the recording for Tuesday?
No, I haven't, because I haven't been able to log in, and it's a big. I can't email him. Because it's a pure recording, right? It's like 100 meg or something.
Maybe you should just call the IT department.
Yeah, that's what I'm gonna do. Okay, so should we carry on with this one? Can everyone see? Yeah. Okay. So did you guys follow the online lecture? Right. So we've yeah. I didn't see many people.
I didn't want to.
Anyway, so we talked about mass analyzers, right? So what we're gonna do is this is one of my favorite lectures, by the way. So what we're gonna do is we're gonna do a bit of a sort of revision here, right? So you remember these are the essential components of a mass spec, right? Okay. So first of all, we need to introduce the samples, then we do ionization source. How do we ionize samples? Soft ionizations. Electrospray and moldy, very good. So these are the soft ionization sources. And then we've got a mass analyzer, right? Or two. And this is what, so we said generate ions, then we separate ions based on their mass to charge ratio. And when was it, Tuesday or whatever, the lecture we had last time, it was all about mass analyzers, right? And do you remember which ones we covered? Out of curiosity? We covered 4, didn't we? A quadrupole? A what? A orbit trap, very good. FTICR, and a time of flight, right? Yeah. So those are the main ones. Now, the thing we're going to talk about today is about tandem mass spectrometry. So this is where you put 2 of them together, right, to form a tandem mass spectrometer. And usually here you've got a collision cell, so the idea is that you select something, you smash it to bits, and then you use a second mass analyzer to analyze the fragments. And this is very, very, very informative, okay? And then finally we've got sort of our ion detection system, okay? So, tandem mass spectrometry, right? So this is abbreviated to MSMS. So sometimes when people say MSMS, that's what they mean. They mean tandem mass spectrometry, okay? So, it's a means by which to obtain the mass spectrum of a mass spectrum. Okay? MS, right? So usually what we do is causing ions to fragment, and then the second mass spectrum reveals this sort of fragment information. So here, let's say we've got 2 ions, different masses. Do you remember we can use here a quadrupole? Because do you remember out of the mass analyzers, I told you the quadrupole, you can fine tune it, so you can isolate a specific mass to charge ratio. So what you can do is you can just select this ion here. You can put it in a collision cell, and we'll talk about how we do this. So you can activate and dissociate it, right? And then the fragments, the bits of this, you then use your second mass analyzer to detect them, to separate and detect them. Now, how we refer to these is precursor. So this is the precursor ion. This is the full ion. And then we talk about the product ions, precursor and product. Now, this is a non-politically correct terminology that people used to use sort of in the 60s or whatever, which was the parent and the daughter ion. We don't use that. The reason I'm putting this is just in case you come across any old school papers and they talk about daughter ions and you're like, what the hell is this, right? Okay, we don't refer to them like that now. So we could talk about precursor and product ions, yeah? So isolation of an ion, Now, you might ask me, well, why don't we just fragment everything together? Yeah? And you'll be right. Nowadays, there are some ways where we can do that. The problem is that it's then very difficult to delineate which fragments belong to which precursor, yeah? And there's been some really cool software, a lot of based on sort of machine learning that does that, but this is a bit beyond this course, right? So for the purposes of this course, we're going to talk about sort of the traditional, the more established method where you have a number of ions, but you select one, yeah? You fragment that one, So then you know that these fragments tell you something about your precursor ion. Okay? Is that clear? Now, again, like everything in mass spec, there's so many different ways of fragmenting ions. Yeah? Again, we're not going to go into all the nitty-gritty details, but we're going to cover collision-induced dissociation, or CID. Now, I am very lucky and privileged. I know the guy that discovered CID. This was Keith Jennings at Warwick, and that's why he's won all the awards in sort of mass spectrometry and stuff. So Keith came up with this idea. So I told you in the first lecture that when we want to do mass spec, we need to have a vacuum, right? We don't want our ions to collide with anything. We want them to go through, have a large mean free path and go to the detector. Well, in this case, you don't. In this case, you on purpose increase the pressure in this collision cell, yeah, in this bit. You increase the pressure, and you also increase the energy by which these ions enter this. So effectively, this ion goes into this region, and there's all these inert gas molecules, so it's not reacting, yeah? So, you know, usually you have inert gas molecules. You know what I mean by that, right? So like argon, yeah? Nitrogen sometimes we use. So they're not reacting with your ion, but what happens is it's a bit like, it's got all this energy, yeah, it's going in fast, and it starts hitting all these small gas molecules, right? And that's what causes the fragmentation, yeah, in CID. So what happens is, if you increase the energy by which your ion goes through, it's going to have higher sort of energy, kinetic energy. So some of its translational energy after these collisions will be converted into internal energy. So suddenly the bonds are going to start vibrating of the molecule, right, after all these collisions. And then effectively, at some point, it's going to cause your ion to fragment, yeah? And the nice thing of this for biological mass spectrometry, as we'll see in a minute, is that peptides fragment very predictably, okay? So that's why it's super useful and super powerful for us sequencing peptides, yeah? Okay? So CID can be used to fragment peptides and therefore obtain their sequence, yeah? Any questions so far? No? Good. So again, there's so many different ways you can put sort of mass analyzers together to come up with a tandem mass instrument. However, you know, one of the earliest and sort of still used, actually, I've got quite a few of these in the lab, is the QTOF. And this has been a very popular mass analyzer. So this is a quadrupole time of flight, right? So the way it's constructed, the geometry of the instrument is that you've got a quadrupole here. And remember what I told you, what can you do with a quadrupole?
Change the
You can change the values and you can basically isolate a particular. Yeah, do you remember we talked about the stability? Yeah? So you can use it as a mass filter. So you can filter out all the other ions and only let one go through, the one you're interested in. Or you can actually don't bother with any of this and just use it as an ion guide, just to put in all the ions through. And then you fragment your ions here, and then you use your time of flight. And do you remember the time of flight is one of these simultaneous transmission ones, yeah? And you remember in the previous lecture I told you about, you know, the equations and, you know, how we measure basically the time it takes to travel in this reflectron, how that is related to the mass to charge ratio, right? Okay? So a QTOF, quadruple time of flight instrument, you can operate that, you can use it in two modes. One is MS mode, where you're not doing any fragmentation. You can say, okay, let all the ions through, don't do any fragmentation, you know, don't increase the collision energy, no gas in here. Boom. And then just use it effectively as a time of flight. Right? Hello? So you can use it as a time of flight and measure everything that's in your sample. Or you can switch to MSMS mode, yeah, where basically you say, okay, I want you to select a particular mass to charge region, fragment that, yeah, and then analyze the fragments using the time of flight. Yeah?
What is the RF?
Sorry?
The RF.
So here I said it's okay. Don't worry about it. But it's called RF only mode. So you don't put any other voltages. You just still have a voltage you basically use it as an ion guide. So you have some voltage to get the ions through, but you're not doing any of this sort of waves and stuff in causing the ions to have this sort of stability. All of them will go through. Okay? Now, I've got this video that can be quite useful actually. Let me just take the volume down to show you how it's working. So this is a QTOF from I've got this in the lab. The company gave the schematics to this graphics design company. So this is, the actual drawing is accurate. Some of the animation, as we'll see, is a bit fantasy, but I'll tell you. So we're looking at it, it's a QTOF, so we're looking at it from the back now. So we're looking at the time of flight, that big tube you saw, it was the TOF, the time of flight. As we go through here, we're going to see there's a collision cell, there's some ion guides. And in a minute, you're going to recognize, hopefully, the quadrupole. Because look, do you remember 4 rods? Yeah? We talked about the quadrupole? And then this is the sort of front end, right? So here is the source where you're going to be doing electrospray. So imagine now, this is what the sort of, a bit fantasy is. So imagine now we've got a number of different peptides. Each one of them has a different mass. So you can see the different colors here, right? Mm-hmm. So here you can see the quadrupole flashing. I mean, it doesn't flash, but, but the idea is that, you filter out all the other ions apart from the red one, yeah? And I mean, if it was realistic, you'd have these very complicated ion motions going through, but, okay. So, you're filtering everything out. So, they're hitting the sides of the quadrupole because they have an unstable trajectory. And then what happens is here, this is the collision cell in here, you can imagine. I mean, they're not showing here that there's gas molecules, but the idea is that the red one is now colliding with these gas molecules, and it's breaking down to smaller fragments. So bits of it are coming off, yeah? So you've got fragments. But you still can have the precursor, because we'll come to that. So now you've got all these sort of fragments, and then you put them through the ion guide, and this is a time of flight. And do you remember we talked about reflectron time of flight, improving the resolution? So this is a reflectron, right? So they're pushed down. You can see they're going down now through this grid, and they're coming back up to the detector, right? I mean, this is complete fantasy. This is Hollywood. It doesn't look like that. I've shown you what real spectra look like, yeah? Everyone happy with how we do MSMS, yeah? Okay? So yeah, as I said, this is super fantasy. This is what this is what data looks. This is real. Okay? So let's take an example, because this is what we're going to be talking about. So you guys, I assume, but correct me if I'm wrong, you know what proteins are, right? Yeah? How do we make proteins? Amino acids. Very good. So we've got the amino acids. And what happens? How do they come together? Condensation, right? So you have 2 amino acids, and they lose water effectively. And they form, what do they form? The peptide bond, yeah? The peptide bond. Okay, good. That's really good. Now, have you heard of this enzyme called trypsin? Because this is super important for us. Yeah, so it's in your stomach as well. So you chew your food, obviously, and it goes to your stomach, and your stomach is very acidic and stuff. But there's also enzymes, right? Well, no, in your stomach you've got pepsin, but anyway, the concept is that you've got enzymes that chop other proteins into smaller bits. Yeah, they don't necessarily. Some of them go down to amino acid level, but what they will do is they will take your protein and they will cut them to smaller bits. Yeah, so you go from a sort of protein to sort of peptides. Yeah, okay. So for the rest of this course, and for the other lecture as well, when we're going to go into sort of proteomics, most of the times we don't just put the intact protein into the mass spec, right? When we say we sequence a protein using mass spectrometry, we don't just put the protein. What we do, we take the protein and we use trypsin, and we use trypsin to cut it to smaller bits, yeah? Now trypsin cleaves quite frequently, so what you do is you get peptides that are around 7 amino acids long, yeah, in length. And once you do that, that's the stuff then you put into the mass spectrometer. Okay? So usually the way we do this experiment is if you have a protein, you cut it, digest it into peptides. You don't necessarily put all of these peptides straight into the mass spec. You use liquid chromatography. Now, did you cover HPLC, I think, with?
Yeah.
Did you cover reverse phase HPLC? Yeah? How does reverse phase work? What's the principle of separation?
Phase would be non-polar.
Sorry?
Restriction phase would be non-polar and
Polar mobile phase.
Anyone else?
Sorry.
Yeah, you're getting there. That's close. But what's the principle? It doesn't separate them based on charge, does it? It separates them based on?
Size.
Nope. That's size exclusion.
Polarity.
What polarity? What's charge, right? Hydrophobicity. Does that ring a bell?
Yeah.
Hydrophobicity. Do you know what that means? It's a Greek word. I'll help you.
How likely is to
The water.
Do you know what ether is? Ether is an old school word for water in Greek. And do you know phobos? There must be like a Marvel superhero, phobos or whatever. That's fear, right? So hydrophobicity means fear of water. And the opposite is hydrophilic. What's philos? Is my friend. Philos is my friend, right? So hydrophilic is, yeah. So how does reverse phase work? So you put a mixture of peptides. Some of them are going to be hydrophilic, right? Some of them are going to be hydrophobic. So they all bind to the column, right? How do you get them off? So you bind them on the column, on the stationary phase. How do you get them out? Hmm? Mobile phase. What's the mobile phase? But what is it? Water.
Yeah.
Excellent. So you pass water through the column, right? So which peptides come out? The friend ones, right? The friendly ones. They're friends with water, so they come out.
Yeah, exactly. And the others are.
And then how do you get the hydrophobic out?
Other substance from other solvent in a mobile phase.
Through selective retention.
Sorry?
Through selective retention of the hydrophobic.
So the hydrophobic, you're absolutely correct. They will have a later retention.
Yeah.
But what I'm saying is, how do you do it? So you start with water, yeah.
Then later we change the gradient with the other mobile phase. Like
So what you do is you have two
mobile.
solutions. You've got a water, and then you've got an acetonitrile, which is right.
Yeah.
And what you do in these HPLCs, you start making a mix. Yeah, you start with 100% water, and then you slowly ramp up the amount of acetonitrile. It doesn't have to be acetonitrile. We usually refer to it as organic. Yeah. And again, by convention, you'd have like if you had your HPLC, you'd have your sort of mobile phases, right? I'm terrible at drawing, by the way. But you'd have your sort of A and B, yeah? Your A would be water, yeah? And this one would be your organic, yeah? Okay? And then what you do is here, this is time, right? So this is going to be your elution. And you're monitoring here the UV, like absorbance, right? So what happens is here you're going to start getting your sort of hydrophilic peptides, and as you go on, you're going to start seeing your hydrophobics, right? But if you overlay here the gradient, usually we do the percent B, if you look at it, right? So you'd have something like this, sort of 0 to sort of 40. You never go to, yeah? And then you do a gradient, yeah? You start ramping up. And then suddenly at some point you might go really high to wash off sorry. So here you then do a wash. Do you know what I mean by that? A wash would be really crank up the organic to like get rid of everything. And then you recalibrate for a bit and then you start another round. Yeah? Okay? So in our case this is what's gonna happen. We're gonna have we're going to have a protein, yeah? Let's say this is our protein, yeah? We would have cut it with trypsin. So as we'll see in a minute, trypsin cuts after arginine or lysine residues, yeah? So if you had something like this, trypsin will go in and it will say, okay, I found a lysine, cut it, arginine, cut it, cut it, cut it, yeah? So then you get all these different peptides, yeah? And that's how you start separating them, yeah? And as we'll see now is how we're going to sequence them, okay? Is this clear? Yeah, good. Okay, so this is what this is basically showing you. So what happens is at each point in time of that sort of elution here, yeah, the mass spectrometer does what we call an MS1 scan. Remember, we've got two mass analyzers, MS1 and MS2, yeah? So what the first mass analyzer often does is does a full scan. So what it does is says, have a look at all the peptides that are coming off the column at this point. So there might be like a lot of them, yeah? It says, have a look at all of them. And then what it does is, and usually this now happens automatically. We'll revisit this in the other lecture on the proteomics. But usually what it then does, it says, okay, go and rank these peptides as to which one is the more abundant, yeah? From highest abundance to lowest abundance. And then what it does is go to the most abundant, and then it isolates it, yeah? It fragments it, obtains the MSMS spectrum, and then it goes back and goes to the second most abundant, fragments it, sequences it, and then goes back. And it does that for the top 10, let's say, yeah? And once it's finished, it goes back and says, okay, what peptides do I have now, eluting from the column? And it does that. And it keeps going and going and going. So over an LC gradient, you might get so many, like hundreds of thousands nowadays, MSMS data. Yeah? Okay, so that's good. And then this is what the MSMS spectrum looked like. And this is a real life example. Okay. So the spacing between these peaks. So if I told you, like you told me that peptides form by condensation, yeah, by two amino acids coming together and forming a peptide bond, right? So if I told you that the peptides fragment on the peptide bond, yeah, what would be the difference between two adjacent peaks, do you think? What it correspond to? Okay, don't worry, we'll come back to it. Right. So I assume you guys are familiar with this, right? So this is a depiction of a 5 amino acid peptide, yeah? I've put here a general depiction because we've got, depending on the R groups, we have different amino acids, yeah? But I'm showing here the backbone. So we always go N-C alpha C, yeah? So this is the C alpha bond, yeah? So out of all these, which one's the peptide bond? I always get confused. Which one is that?
Between the carbon and the nitrogen.
This one?
Yeah.
This one? This one? Yeah? Great. So we're going to have a fragmentation here, yeah? So all these peptide bonds could theoretically fragment. However, because of the process of the CID, which is, we call it a slow heating approach, the way it does all these collisions slowly, some of this sort of kinetic energy starts becoming vibrational energy. Because of this, in CID, we only fragment the peptide bond. Yeah, so you don't have to worry about the other ones. Now, I'm drawing this again from, we always draw peptides, from the N terminus to the C terminus, right, by convention. So we've got all these different bonds that can fragment. And here I'm highlighting, this is the peptide bond. Yeah, this is the one we're interested in. Okay. Now, when people started doing these experiments, they needed to come up with a way of communicating with each other as to what fragments they've got, yeah? And this is the nomenclature. It's nothing, there was not much thought put into it. I've actually heard the guy that came up with this nomenclature. He just basically said to his student, just name them A, B, C, X, Y, Z, right? And get it over and done with. But you need to understand how they're named in order to do what we need to do here, right? So it's very simple. You have A, B, C ions. Yeah, can you see how I've got these sort of lines following? So I'm showing you where the bond, which bond fragments, yeah? And then I've got this line. Now, why do I have this line? Remember we said that everything in mass spectrometry is charged, right? Hello. Now, especially protonated, yeah, because we're talking about electrospray. So imagine, to see this peptide as a precursor, it has to be protonated, right? Now, imagine there's only one proton, okay? And imagine that the peptide fragments on this bond, right? But you've only got one proton, yeah? Well, which bit are you going to see, this bit or this bit in the mass spec?
This bit.
This one?
Yeah.
Why?
Because that's what it's protein.
Okay. Anyone else? Let's vote. I like voting. Who thinks we're going to see this bit? Why doesn't anyone like this bit? Who thinks it's going to be this bit?
I'm thinking this is
You change your
because I think it's more
You
polar.
change your mind, right?
Yeah.
Yeah. Who thinks we're going to see none of them? Who thinks we're going to see both of them? Okay, great. So what happens is, and this is something that took me a while to figure out when I was studying in mass spec. When we isolate a particular charge state, let's say we see one peak, right? It's not one copy of that molecule. There's multiple copies of this, right? So you've got many copies of this peptide that's singly protonated. Now what happens is, sometimes that peptide is going to fragment here, yeah? And the proton will end up on this bit, on the N-terminus. Yeah? When that happens, you're going to see this bit of the molecule, this fragment, which we now are going to call the B1 fragment, right? Some cases, though, the proton is not going to be here, it's going to be here, on this part. In which case, you're going to see this fragment, yeah? And this is why now I've got this kind of line, yeah? So the lines basically tell you where the sort of charge has been retained, yeah? On the
Is
C
there a
terminus.
possibility that we have the two at the same time?
We're going to keep it simple here. If you have one proton, there's only one chance, right? But in some cases, you're going to see you're going to see this ion. In some cases, you're going to see the other one. Yeah, out of all the copies, you're right. Now, it's slightly more complicated if you have doubly charged peptides or triply charged peptides and stuff. But again, you know, let's not get confused here. Okay? So do you get this concept, right? That you've got many copies. Sometimes it's going to break on this bond. Sometimes it's going to break on this bond. Sometimes it's going to break on this bond. Yeah. But depending on where the charge goes, then you get either A, B, C ions. Yeah. So the ones where the charge is retained on the N-terminus are called A, B, C ions. Yeah. The ones where the charge is retained on the C-terminus are called X, Y, Z ions. Yeah. And the only thing you need to remember is and this is confusing sometimes. You start numbering, 1, 2, 3, from where the charge has been retained. Yeah? So for the B ions, it's going to be B1, this bit, B2, this bit, B3, this bit. Yeah? Well, for the Y ions, it's going to be from here. So it's going to be Y1, Y2, Y3. Yeah? Nice? Right. Now, I'm going to ask you a few more questions. If you answer these questions, you're golden. You've solved everything, including one of your coursework. So, let's say we've got this this particular amino acid sequence, yeah? Okay, yeah? Okay. Now, imagine another, it's very imaginative, nice lecture. Very philosophical. I'm Greek. What can I do? So imagine you only had B ions. So what are the B ions we said? Where the proton is on the inside. Exactly. So forget the other. Imagine you've only got B ions, right? So in this nomenclature, if we had this sequence, this would be the B1 ion, would be this bit, and the molecule. It's fragments. It's a piece of the full. B1, B2 would be this bit, yeah? B3 would be this bit, yeah? B4 would be this bit, yeah? So if I write them here, B1 is A, B2 is AI, B3 is AIT, yeah? B4 is AITW, yeah? What is the difference between two consecutive ions?
The difference in what?
So, what's the difference between the B2 and the B3 ion?
Addition of the amino
Will
acids.
be
New amino
this
acids.
time.
Plus one.
One amino acid.
Extra.
What's the difference between the B3 and the B4? One amino acid. What's the difference between B1 and B2? One amino acid, right? So, if you had a mass spectrum, the B1 is small because it's only one amino acid, yeah? So, and as we'll assume for this lecture, everything is singly protonated, right? We're going to keep it simple. So, if this was, so where would it be? Where would it come out? Here or here on the mass to charge scale? Near here or near here? This side?
B1. For B1.
Yeah, the B1.
This side.
This side, exactly. This is the mass to charge scale, yeah? So you go from sort of 0 to 4,000, let's say. So it's gonna be here. Where's the B2 gonna come?
Next to it.
Yeah? Here. What's the difference in mass between the two? What is it gonna correspond to?
That will be mass about charge 1/2.
Sorry?
1/2.
So the difference between them is gonna be the mass of
Right.
one amino acid.
Yeah.
So the B3 is going to come here. Again, what's the difference between the B2 and the B3? The different. If you took this mass and took out this mass, one amino acid. Again, the B4. Yeah. So if I gave you a spectrum and it only had B ions, you could find out the amino acid sequence, right?
Yeah.
Super easy. I'll give you a table, right, of the amino acid masses, but do you get it?
Yeah.
The two adjacent ones are basically an amino acid. Yeah. So the spacing between them will depend on the sequence of this peptide, but that's it, right?
Logical, yeah.
Okay. Now, where does it get a bit complicated? And this is why we're going to spend the rest of the lecture helping you with this. Now, where it gets complicated is that, what did I tell you? I told you that sometimes you'll retain the charge here, right? So you'll fragment here, but sometimes you're here. So here you're going to get the Y1 ion, yeah? So Y1 ion is K. Yeah? The Y2 ion is WK, right? The Y3 ion is TWK, yeah? And the Y4 ion is ITWK, yeah? So here we've got Y1, Y2, Y3, Y4, yeah? Now, the Y1, is it big or small?
Small.
It's small, so it'll come around here, yeah? Y2, let's say here. Y3, depending on the masses, might be here, Y4. So when you actually do the mass spec, so again, what's the difference between two Y ions? It's one amino acid. The difference again between these two is one amino acid, one amino acid. It's very easy, right? So now again, it comes back to what I was saying earlier. If I give you a spectrum and I said to you, these are only B ions, or this is a spectrum with only Y ions, right? You could sequence them. Yeah? You just find the mass differences between the two. Is that, yeah? Good. Now, the challenging bit is that all these things are happening at the same time in the mass spec. So what you do is you get fragmentation across all bonds most of the times, and sometimes you get B and sometimes you get the Y ion, right? So when you get a spectrum, it's not nicely colored like this, you just get peaks. And you don't know whether they're B or Y ions. If you knew that they were B or Y ions, you do this, it's very easy. But you might have a B ion next to a Y ion, or you might have a gap, or whatever.
And how do you distinguish that?
Well, that's what I'm going to teach you.
Ah, okay.
Yeah? So most of the stuff we're going to do in a minute is basically trying to get a handle on this. How do we start telling whether something's a B or a Y ion? Yeah? I just want you to understand this. Because if you understand this, the rest is going to become very, very easy. Do you see why this can't be done on Teams? Yeah? Any questions? Is it clear?
So there's no.
No. Where are you confused? Tell me.
Now, I think I need to understand the B and the Y thing.
The nomenclature, okay.
Yeah.
So the nomenclature, as I said, it's basically just if we come back here. So this is the best way to look at this. So this is a peptide. This is a sort of depiction of a peptide, yeah. And you know the peptide bond, right? So it's always going to be this CN bond. So this is always the one that's going to fragment when you do CID, okay? But as I keep saying in all these lectures, if something doesn't have a charge, you can't do mass spec on it. It has to be charged, okay? So if you only had one charge on the full molecule, and then you broke it down to 2, you still have only one charge. Yeah, you can't split the proton. So the proton will either choose to go on this bit of the molecule or this bit of the molecule. Yeah? If it goes on this bit of the molecule, which still has the N terminal, it's called B ion. It's the B ion series. So it's going to be B1, B2, B3, B4. Yeah?
I thought you called them ABC.
Sorry?
I thought you called them ABC.
ABC is because this is the nomenclature. I mean, try to ignore the other ones. The A is if this bond fragments the CC bond. B ion is if it's your CN bond. Okay? Now the corresponding thing of this is the Y ion series. So again, if it breaks here but the charge remains on the C terminal part, the carboxylic part, that's going to be the Y ion series. Yeah? That's all. But the idea that, 2 consecutive B ions or 2 consecutive Y ions, their difference is basically an amino acid. Right?
Yeah. It's not a charge.
Sorry?
Just amino acid.
It's just an amino acid.
Not the charge.
No, because they will be charged. The only difference. Everything in mass spec is going to be charged, right? And as I said, for this purposes, don't worry too much about it, but pretend everything is going to be singly charged. Everything is going to have a single proton. So every fragment is going to have one proton. So the only difference between them is going to be the residue. Yeah? Now the other thing that's interesting is that if you look here, it's not, I think I cover it. Well, we'll come back to it. Okay, so I've talked to you about the importance of basic sites in a peptide. So, we've got a lot of charges, and usually it's lysine, arginine, or histidine residues. But again, as I keep saying, for this purpose, we're just going to keep everything simple and say that everything is just singly protonated, yeah? So now, I'm basically here showing in this slide what we've just discussed here. If you have this particular peptide, maybe this will make it clearer now. So you've got this peptide, and it's singly protonated, yeah? And as I said, sometimes if you break it here, and the charge goes here, you're going to get your Y1 ion, yeah, a small one. And then here, if the charge goes here, you're going to get the corresponding. What I mean by corresponding is that these two ions, the Y1 and the B3, give you the same information about which bond fragmented. It's the same bond that fragmented here, yeah? The sort of corresponding to each other, yeah? So if you then had fragmentation here, you're going to get your Y2 and your B2, and here you're going to get your Y3 and the B1. Now, I've done this in sort of slow motion, but this is what you get, right, in the mass spec. These are all happening super fast. You just get this whole thing, yeah? So you usually get the largest peak being the intact, the precursor, yeah? And then here you get the different fragments, yeah?
So can you go back to the next slide?
Yeah. This one?
So the last one is before R4 double bond proto OH. That's going to be the before.
So here, see here you've run out. So then you don't have any fragments. Then you've got the full molecule.
So we have just 3 here.
Yeah. So here, yeah. So this is a 4 amino acid peptide. So you're gonna get up to 3 fragments. Yeah. Because then the fourth is then the full. Right. If you add the final amino acid, then you've got the full peptide. So it's not a fragment. Yeah. You're right. So we see this, right? But again, we talked about the residue mass, yeah? So the residue mass of an amino acid is the mass of the amino acid minus water, effectively, yeah? So when the peptides have come together to form peptides, they have lost water, yeah? So we're not talking, so you have to take that into account. So you're not talking about the amino acid mass, you're talking about the residue mass, yeah? It's basically the amino acid minus water, yeah? I'm tempted to skip this because it might confuse you, but basically, these are very informative. So we have a class of ions called ammonium ions. So they've got nothing to do with what I've described just now. But basically, this is some rearrangements that happen in the gas phase, and you get these ions that appear at the very low mass to charge ratio, and they don't give you any information about the positioning, but they give you hints that you had a particular residue. So if you have like sort of serine in there, you will get a characteristic 60 Daltons ammonium ion that represents cysteine. It will all come together in a minute because we've got a big sort of, problem that we're going to go through. Now, you're not going to believe yourself, but you will learn how to take simple spectra, MSMS spectra, and figure out their amino acid sequence by hand. You will, trust me. I don't know how many times I've done this course and how many everyone looks at me like I'm an idiot when I do it, and by the end everyone really enjoys it, okay? So it looks difficult, but it's not, trust me, yeah? I'll give you all the tools. So anytime I ask you to sequence something, yeah, I'm going to be nice. I'm going to give you simple spectra, so there's going to be no noise and anything like that. Everything's going to be singly charged, and all the peptides are going to be triptych peptides, yeah? And that's important, okay? And also I'm going to give you something like this. So this is a table that has the amino acids, yeah? It's got the name, the 1-letter code, and then it gives you the residue mass, yeah? And then here it gives you the ammonium ions, these weird ions that appear at the low mass to charge ratio. It gives you the mass of the ammonium ions and whether they're observed frequently. You can sort of ignore these, but they're really good, as we'll see in a minute, as giving you a hint of when you start the sequencing process and you don't know anything, whether you have like particular amino acids. Okay? Now, B ions. So we talked about the B ions. So the B ions are formed by the loss of water and successive residues from the C terminus of the peptide. And it's rare that we see the B1 ion, but sometimes we do see it, right? And here, I'm just giving you some very simple calculations of how you calculate the different B ion series. So, apart from giving you a spectrum, an SMS spectrum, and asking you to figure out the sequence, I might give you a sequence, yeah? A, C, C, I, T, R, whatever, and ask you to calculate the different fragment masses, right? And these are sort of the calculations. So it's usually the mass of the residues retained plus the N-terminus group. But again, we're going to keep it simple. In most cases here, we're going to be talking about an N-terminal group of H. Yeah? So that's how you calculate. Now, if we go back here, let's go back. You've got these B ions, yeah? So they retain the proton on this N-terminus. But next to them is these A ions, yeah? The difference between a B and an A ion is a CO group, yeah? Now it turns out when you do CID that you often see these A ions, and that's very good. Why is it good? Because you often see a B and an A ion pair, and their difference is going to be 28 Daltons, yeah? Sorry, I'm coming back, sorry. Yeah? So you've got a B ion pair. So you can calculate the B ions, and then the A ion is going to be minus CO. Yeah? So it's the mass of the residues retained plus N minus the CO group. Yeah? And as I said, it's very useful during the sequencing process. Yeah? Because you can pick up these sort of doublets. Yeah? And then we've got the Y ions that we talked about. So it consists of ions that lose successive amino acid residues from the N-terminus of the peptide. Yeah? And during the formation of Y ions, 2 hydrogen atoms are transferred to the ion from the neutral species. Okay? That's how it is. So therefore, the mass is going to be the mass of the residues retained plus the C-terminus now. And in our case, the C-terminal group is going to be OH. Yeah? Simple. We haven't modified our peptides, so it's going to be HOH plus H2. Okay? Simples. Now, comments. So, leucine and isoleucine, if we do CID, low collision induced CID, we can't differentiate them. Do you know why?
Same mass.
They're isobaric. Absolutely. They're the same mass, so you can't tell. Yeah? So if you sequence and you come across a leucine or isoleucine, you think it is, you can just put that, or you can put an X. Yeah? And also there's another thing that happens after, people have observed the fragmentation of thousands of peptides, is that at the N-terminal cleavage of a proline residue usually increases the Y-ion intensity, and they've called this the proline effect. Yeah? Right. We'll come into the really exciting bit in a minute. Any questions? No? Okay. So so next to it is a table that Keith gave me. You remember Keith, the guy that discovered CID. He gave me this sort of cheat sheet, if you want. It's how do you sequence a spectrum? Yeah? What are the steps to follow? Now, you don't necessarily have to follow this. You can go another way. But what I'm going to try to teach you is I'm trying to teach you all the rules of the game. It's a game, right? It's a game with constraints. Yeah? Have you played Sudoku, anyone? Yeah? So you know Sudoku, you've got the constraints, right? It has to satisfy certain, and that's how you solve it. Well, the way I see this is a bit like that. So I'm going to give you all the hints, and then it's up to you how you go and do it. But usually, it's always good to sort of have a feel of how many amino acids you've got. So if you take the precursor and you divide it by 110, you get a feel of how many amino acids you've got. And that's why, because 110 is like the average mass of a amino acid, right? It's not conclusive, yeah, but it gives you a feel of how. Then you can look at the low M over Z, and you find ammonium ions, yeah? Now, you shouldn't stress, if you don't find any of it, it doesn't mean anything, yeah? But if you find something, it's another constraint, yeah? If you find the ammonium ion, for serine, and then you go and you sequence, well, you'd expect that some... So the ammonium ions are these weird, let's go back, these weird ions, these ones. They basically form, again, don't worry about the structure, but basically these form in during the fragmentation process, right? So they're always going to be at the low M over Z, and this is their mass, yeah? But what I'm saying is if you find a 60.045 peak in your spectrum, that tells you that there should be a serine somewhere in the sequence. So when you carry on sequencing and you find a serine, you're like, okay, this makes sense. Yeah? But if you don't find them, don't worry too much. Now, Keith loved this B2 ion. So the B2 ion is quite stable, so we usually always observe them. And the B2 ion is basically going to be, the residue 1 plus residue 2 plus 1, yeah? The proton. Okay?
First fragment after that.
It's the first two amino acids, right? And again, you don't need to remember their mass. I'm going to give you this table when you sequence them. So we'll come back to this. So this one is a B2 ion combination. So, valine glycine is 157, yeah? Cysteine glycine is going to be 161. So the way you use this is you find peaks in your spectrum. Let's say you look at a sort of 214, yeah? So you scan this and you're like 214. Okay, 214 is arginine, glycine, or 214 is, where is it? Asparagine, valine, yeah? So it gives you like potential combinations. Again, that's another sort of hint, right? The other thing I told you, the B2 ions usually have the A2 ion, yeah? And their difference is going to be 28 Daltons, yeah? So again, if you look at two peaks and the 28 Daltons difference, it gives you a hint, yeah? That this is B and A ion. What did I tell you over there? If you only had one ion series, it would be trivial to sequence this, right? You just go from peak to peak and figure out the sequence. So all this stuff I'm teaching you here is trying to get a handle on what's a B, what's an ion. Now, if you've caused a fragmentation, look at the board here. If you've caused a fragmentation here, AI, and you've got the B2, you also have which corresponding Y ion? The Y, what is it? Y3. That's the corresponding ion, yeah? So if you identify the B2 ion, you might find in your spectrum the Yn minus 2 and Yn minus 1 ion, yeah? Now, if you've done a tryptic digest that we talked about here, so you use trypsin to make your peptides, which is what we'll always do in this course, your C terminus is going to be either a lysine or an arginine. So that's easy because a lysine Y1 ion will have the mass of 147, and arginine Y1 ion is going to be 175. Yeah? So that's another good hint of, okay, this is my Y1 ion. Yeah? And then it's easy. Right? Then you just go from peak to peak, you calculate mass differences, and you keep looking at the table I've given you of the residue masses, and you try to find mass differences. And if you find one, if you go from your B2 and you find another peak, well, that's the B3, and then B4. Or vice versa, if you find your Y1, and then you go up, the other one's going to be your Y2. And your Y3. Yeah, then it's easy. Yeah? So again, remember, these A ions are usually seen 28 Daltons below peaks. Now, cleavage of the N-terminal side of a proline will intensify the Y ion, and that's it. And that's the B2 ion combination. And here's a spectrum, a very simple spectrum that I've made. So, do you want a 1 minute power break? Because you need to focus on this. Once you've done this, golden.
How many residues are there in this trypsin cleavage?
So the average, so when people have sort of digested whole proteomes and they've calculated that, the average length you get is 7. 7, yeah, so sort of from 5 to 13, that's about, the peak is sort of 7, that's the average. Yeah. So you didn't get really, really long ones, yeah. And also, real spectra look more difficult than this because you have you get noise and stuff. But any questions or no?
If you find a specific ammonium ion, does it necessitate that you always find the corresponding residue?
You should find a residue, yeah. Otherwise, that wouldn't have not formed. But the ammonium ion doesn't tell you where it is. It just tells you that it's there. Yeah? Okay. Ready? Should we do this? Let's do it. So, how would you go about this if we apply the sort of rules that Keith told? So let's see. So we've got, this is the precursor mass, yeah? So this is the full peptide protonated, and these are all fragments. So how many do we think we've got roughly? Well, 434 divided by 110, 3.9. Wow. So that means we've got between 3 and 5 amino acids, right? And again, you don't have to do this, but it just gives you a ballpark idea. Yeah? So the next step was identify the ammonium ions if possible. Absence not conclusive. Yeah? So you start looking at this. If you go back and you look at the ammonium ions, they go from 30 up to 160, yeah? So they're at the very low end of the spectrum. So you go down there and you're like, there's a 60 here. And if you look at the table, that will indicate the presence of a serine. So you write that, you're like, okay, I probably have a serine. Now, as I said, Keith loved this sort of finding the B2 ion, right? So this is sort of the region you'd expect the B2 ions. I mean, they can be a bit higher as well, but you start by this. So this is the thought process. So there's many masses that could correspond to the B2 ion. So the 161, yeah, could be a CG or a GC. You don't know you don't know. It's just the mass, right? It could be CG or GC. You don't know. The 175 could be a CA, and the 189 could be an ST. Yeah? But again, this is where the constraints come in. But what else did we say? We said that the B ions usually have an A2 ions, yeah? 28 Daltons lower. So if you look at the difference between this peak and this peak, it does happen to be 28. Yeah? Mm-hmm. So this gives you another hint that this is probably a B2 ion, A2 ion pair. Yeah? Now, if you do this assumption and you carry on sequencing and it doesn't work out, don't feel disheartened. It can happen, right? You just then have to go back and say, okay, that was not the right assumption. Yeah? But in this case, we get a lot of hints, right? So it's probably the B2 ion. So, and we've got S or T or TS. So that's our B2 ion. Okay? Now, what did I tell you? If you have the B2 ion, so if you fragmented your peptide at the second position, you can have the corresponding Y ion. Yeah? So what you do is you then can calculate the yn minus 2, we don't know how many residues we've got, would be 434.32, which is basically the mass of the precursor, plus 1 minus the B2 ion. Yeah? And that will give you a mass of 246.23. Do we have that in the spectrum? Well, close. Yeah? We've got a 246.16. Again, remember from my previous lectures, it's accurate, but there's always a mass error, right? So this is good enough, I would say. So this now gives you a hint that, so now you've got so many constraints. You've found a serine ammonium ion, yeah? You've got an A2, 28 Daltons lower, and you find the corresponding Y ion. Well, that's quite good, right? Yeah? That's a lot of constraints. Yeah? There's a lot of hints there. So you're happy. You should be happy if this happens. I know you're not, but you should be. Okay? And also the other thing I told you is that we've got triptych peptides. So you were either going to have an arginine or a lysine at the C terminus. And, if it's a lysine, it's going to be 147. If it's an arginine, it's going to be 175. Yeah? Well, you have a 175.12. So that's good. So that probably tells you that the 175 suggests that the peptide ends in an arginine, and the Y1 ion is an arginine. Yeah? So you've done a lot of work so far, right?
What is the range of acceptance of the numbers?
What do you mean?
For
the
example,
mass difference. You
no,
mean?
no, here, for example,
Yeah.
in a spectrum,
Yeah.
if I have 175.75, for example, do I accept or I have to go back? And
I would
go back?
not accept. I would
So
I would
what's
keep
the
it to point.
limit of
Well,
acceptance?
I don't know what I've given you, but I think everything should be within sort of 0.1, 0.2 Daltons. Yeah. And if like nowadays, it would be even less than that. But yeah. But that's a good point. So basically now you grab a coffee and you say, okay, where are we now? Let's take stock. Yeah? So what we think is we've got the S here, right? We think this is the A2, the Y1, the B2, and the YN minus 2. Yeah? So what we think we've got so far from a sequence point of view is S or T in the first position, S or T, we don't know if it's ST or TS, yeah? X or many X's, we don't know, and then R, right? Yeah? And now is the easy bit. So now you go from, you choose now, so you say, okay, this is a YN minus 2. What's the mass difference between this and this? Now if you do the math, it's tiny. It's 14 or whatever. There's no residue mass correspond to that. If you do the mass difference between the next available peak, you're going to find out that it's 101.4, which if you look in your table I gave you, corresponds to a threonine. So if this is the YN minus 2, which ion is this? The YN minus...
Plus T.
Huh?
N minus 2 plus T. T residue.
Yeah, but in number. So if N is the total, huh?
N minus 1. N minus 1, yeah.
Exactly. So this is your N minus 1. So now this is a YN minus 1 ion. And then here, the difference between this one now and the full peptide, if you do the calculation, is 87.12, which corresponds to a serine residue. Yeah? That's great. So now we have a sequence of S, T, X, R. Yeah? Now, you've gone this way. You've started walking this way on this ladder. Now let's go this way. Again, the mass difference between here and here is tiny. Yeah? There's no residue. Between here and here you wouldn't go because this is a B ion. Yeah? You need to find the next Y ion. So the difference between this one and the Y1 ion is 7104, which corresponds to an A. Now if this is Y1, which one's this? The Y? Y2. So N equals? So this is Y1 and this is Y2.
3,
N equals 4.
4,
Yeah, 4 divided by 2 is 2. Exactly. Okay? So this is now your Y1 ion, your Y2, your Y3, and your Y4. So the ones that are unexplained is this ion here and this ion. So you've done the Y ion series. So now you're like, okay, let's go from this one. So this is the B2. So is the B3 this one or this one? Yeah? This difference. So again, you do the math. And basically it turns out that the difference between this peak and this peak is 71.03, which is an alanine. So that's great. So this is your B2 and this is your B3 ion. And boom, you're done. Yeah? So remember, when you're looking at B ions, because you're going from N to C terminus, you can actually read the sequence of the peptide, STAR, yeah? If you're looking at the Y ion series, it's the reverse, right? Yeah? So it's going to be STAR, yeah?
Can you go to the previous slide?
Yeah.
This S ammonium ion is like for the starting point.
Yep.
So for like another spectra is something else, okay?
Mm-hmm.
But the last difference should be the same residual value of that first ammonium ion. That's like
No, so forget the ammonium. The ammonium ions don't give you positional information, so they're not going to correspond to any of that. Don't worry about
It's not a point in stars, no.
it. Just gives you a hint that you have serine. It doesn't tell you anything about the position of where the serine is.
this ammonium ion. Like
Don't get
60
confused because S is the first one as well. Don't get confused with that. It just tells you that you have a serine somewhere in your sequence. It doesn't tell you where.
Oh,
Yeah.
but because we got that last difference.
Yeah, but
with
it's
S,
not. It's
so
not. That's a coincidence that you got the serine.
This is a
Yeah, that's a
coincidence,
coincidence.
not
Yeah,
the-
yeah.
For the same.
No.
Okay.
The ammonium doesn't give you positional information. Now, if you go back to the final solution, if ignore the Y ion series. So in the Y ion series, you had a full coverage. You had STAR, yeah? You've got the full thing. If you look at the B ion series, what's missing? Sorry? The B1. The B1. So if you only had there's a reason I'm asking you this. If you only had the B ion series, right, you would not be able to tell whether it's ST or TS. Yeah? You just have the mass of both of them together. You don't have positional information. You need the B1 to tell the difference of B and R. The reason I'm saying this is because sometimes when you sequence stuff, there is going to be a gap, right? You don't always get full fragmentation. You don't always get full Y ion and full B ion series. Okay? Ta-da! Questions? Now, how much appetite do you have? Like, how awake do you feel? Or how tired?
I'm curious, but I don't know how curious I am.
How much you want to pay for that curiosity? I'm on 4 hours sleep, by the way. My son last night was not happy. Anyway, let's finish this now. Let's see how it goes. So difficulties in interpreting MSMS spectra. Okay, so this is what I told you. In reality, it's going to be more complicated. You're going to have noise. You're not going to have a full ion series or whatever. Sometimes the masses are very similar, so you might not be able to differentiate them. But nowadays, if you have a high-resolving instrument, you should be able to. Leucine and isoleucine is a problem, as you said. They're isobaric. You can't do anything about them. And you'll ask me, well, there's all these software now that can do that. And there's even sort of people that have been trying to feed a lot of these spectra into machine learning models to come up with prediction models. And that's true. But I think it's always really important to still understand why, how it actually works, right? Rather than going into a sort of black box, right? And believe it or not, this has helped me a lot in my career because this is fragmentation of sort of simple amino acids, but then we did a lot of work on figuring out how cross-linked peptides fragment, right? So all this knowledge was directly relevant, right? So there's still... Anyway, what I was going to say is, I've got another example here, so we can go quickly through it. Yeah? And then one of your coursework is, I need to come up with one of these stick data, and then it'll be fun, right? Grab a coffee one afternoon. Yeah? It's like doing the Sudoku, as I told you. Okay, let's go through this. So this is obviously a bit longer, right? So let's do it together quickly. So you identify the precursor, right? Divide by 110. We've got about 8 amino acids, so this is a bit longer. Yeah? So you look at the ammonium ions. Do you find anything? Yes. The 86.1 would indicate the presence of a leucine or an isoleucine. Okay? Great. Then we've got the same thing. Oh, is there any B2 ion here? But what else? Like, what would you say about the whether it's the Y1 ion? Do you remember the two values that we've got? We've got 147 for lysine and 175 for arginine. So we already have a hint that we probably have a lysine here, right? But if you look at the table, there are many masses that correspond to the B2 ion. So the 143 could be AA, the 171 could be G or Li. But also, again, we've got the B2 ion, 20 total is lower. So most likely it's the 171, yeah? And also we had the ammonium ion that was like IL, yeah? So this is probably now our B2 ion, A2 ion, and then once we've got the B2 ion, we can then try to see, okay, do we have a corresponding Y ion? Again, we do the calculation. This is the mass of the precursor plus 1 minus what we think is the mass of the B2 ion. 654.31, 654.32. Good, we're good. We're golden. And then again, it's a triptych peptide. So this probably tells us that this is the Y1 ion and it's in lysine. Okay, so we take a bit of stock. So now we think we've got something like this. Yeah? And then we just basically try to find differences. Yeah? So 654 minus 525, 129, which corresponds to E, which is great. So then you start walking. So what's the difference between here and here? It does correspond to a difference actually, which is glycine. It's the smallest amino acid. Great. The difference then between here and here, again you just do the calculation, corresponds to threonine. That's great. Mass between here and here, 163.07, corresponds to a tyrosine. Amazing. And then from here we end up in a Y. So that's good. That's comforting because if you didn't figure out a mass yet, you'd be somewhere wrong, right? So this corresponds to residual of G. So basically, the yn minus 6 is the y2, which makes n equals 8. So we've got 8 amino acids, yeah? Again, you take stock, and so far you've got this sequence. Oh, and then you go from here, so you correspond. There's a lot of glycines here. What's going on? And then you go from here to the actual intact, and you find a leucine or isoleucine. And that's good because you've identified that from the B ion and from. No, it's a coincidence. Yeah, you're right. So you've got this, right? And then we've got a few unexplained peaks, yeah? And if we look at the 458 and the 430, there's a 28 Daltons difference, which would give us a hint that it's a B-A ion pair. Yeah? The same with the 621. Peak would correspond to sort of a B ion. And then basically you just finish now. Yeah? And that's now you've annotated everything. And this is what you get. So you can't tell whether it's a leucine or isoleucine, yeah, because we can't differentiate them. But it's that G, E, G, T, Y, G, K, yeah? And you can see here that there's 2 ions missing. You've got the B3 and the B4 ion missing, yeah? And that might be the case. Sometimes you might not be able to have a full ion series. But that's it. Full Y series, and then a missing in the B. But you still, the aim is not to find all the ions. The aim is to find the sequence. Yeah? And that's it.
Do we know what the protein is? Do we know what's been in it?
So what happens with this now? So I told you, when you do this proteomics experiment, you sequence hundreds of these, right? So what happens is then that's where a lot of bioinformatics comes in, where what they do is they try to sort of assemble the most probable list of proteins based on your peptides. So you try to do like infer which set of proteins would have given rise to these peptides. There's some really the bioinformatics of how you do this search is quite fascinating. I will touch upon it a bit in the next lectures.
That provides a whole new set of clues.
Yes.
I mean, would that be on the whole that be sufficient to complete the sequence to identify?
Yeah. I'll show you, as I said, in the next one. So what I think I've done now with you guys in the 3 lectures is, I've given you a sort of full overview. As I said, it's very complicated. We'd probably need another 10 lectures, but you know about ionization techniques, right? You know about the mass analyzers, and you know about tandem mass spectrometry, right? So now, what I want to do in the next 2 lectures is spend 1 lecture on sort of high throughput proteomics, so applications, so real life, how do we use it for proteomics workflows, and then the final one is more my research area, which is how we then use this type of stuff in other workflows to look at the structure of proteins and the dynamics. Yeah?
Is that going to be a practical?
Sorry?
Are we going to have a practical session too?
Well, I'm gonna make one of these and try to put it on Moodle. Now, do you want to do it with me? I don't mind.
Yeah,
Yeah,
because
absolutely.
Yeah? So do you want to do it in the next one? So what I'll do is okay. So for the next lecture, I'll go through my lecture, and then we'll do it together. You start sequencing and I'll hang around and we'll all work it. Is that, yeah?
Yeah, that's fine. Thank you
And
so
then we
much.
can give you, the beauty of this, I can keep making sequences, man. Yeah, so then you can have another one for your workshop, because Philip asked me that you need to have some coursework as well. And I think this is nice coursework because it's easy, like you can nail this. You can, yeah. Yeah? Should we do that then? Okay. Okay, good. As I said, even if I don't have Moodle access, I'll get Philip to upload them, but hopefully I'll get somewhere with IT. And I've got a video now, so I've been recording this, so I need to find a way of uploading that as well.